Ja. Sehr schön.
Genau. So, Ton, naja, wird schon irgendwie klappen.
So, I wish you a good afternoon. Now we hear the talk analyzing a modern cryptographic RFID system from Milos Merjak and Henrik Plötz. I know these guys do a lot of RFID research. I also saw their talks last year and year before, and it is promising to be very interesting. So give them a warm applause.
Ja, hi. Hallo? Hallo? Mikrofon? Does this microphone work? Okay, I don't hear myself, but whatever. Yeah, the last year and the year before, and I think even the year before that, we talked about RFID systems, different RFID systems each time, and those were old systems using proprietary or no cryptographic mechanisms at all. This year we want. Yeah, I'm speaking quite loud actually. That's what. Huh? Does this work better? Test. Test. Yeah, now I'm screaming and I don't know how long I can scream. Okay, so this year we want to talk about a proprietary RFID system, HID I-class. I just noticed it's not on the title slide, so let's skip to the next slide. HID is an American company founded as huge identification devices, and they have two systems, one old. We demonstrated a break of the old system, the HID prox, last year, which was not developed by us, but by a friend of us, who was not allowed by HID to present his findings in America. And this year, we want to talk about HID I-class, which is their supposedly new system. It is on a high frequency, 13.56 megahertz. It is almost ISO 15693. It's an ISO standard. And it has more functions than the old system. It is writable, whereas the old system, which is only read-only. It has an electronic purse function, and you can store multiple applications on it, and it claims to have DES or triple DES security, and that's why we wanted to look at this, because this basically is one of the first systems to claim DES security, and we wanted to look how that is implemented, if that's correct. So one of the most important things when you talk about HID, as I said, the company was founded quite a long time ago, and especially in the United States, there are a lot of legacy installations. And if I want to talk about these, I assume most people here will not know that, so I'll have to introduce it. One of the words that you will encounter repeatedly is Wiegand, or I'm not sure the Americans might pronounce that Weigand. It's Wiegand, it's a person, John Wiegand, who was a scientist or is a scientist who had discovered a particular interesting physical phenomenon in specially produced wire. If you take this specially produced wire and give a changing magnetic field on it, it will emit electromagnetic pulse. And the application of this in access control, this was in the 70s and 80s applied in access control to build specially formatted access control cards, which is why you will hear a lot today and you will read a lot in the HID literature about the Wiegand format, which was used on these cards and is used today still. And together with the Wiegand format, you will see the Wiegand interface and Wiegand protocol that are used between the reader at the door and the security panel. The security panel is another of these words that you don't know, or panel is another of these words that you normally don't associate with the functionality that it's associated with in HID speak. The panel is basically the backbone, the backend system. That's what makes the access control decisions. So the reader is more or less dumb and just outputs the number in VGAN format using the VGAN interface and protocol, and the access control panel will then make the access decision whether this person is allowed to enter through this door or not. This is an example of one of these cards. These were pretty simple. They had 2 tracks, one for zeros and one for ones. And these are little strips of VGAN wire. And basically it's just swiped in front of a changing electromagnetic field and then exhibiting the special VGAN effect, which will then allow them to construct a reader that's very simple electronically, because you only need a changing electromagnetic field and 2 coils to pick up the pulses that are output by these wires when they are swiped in front of the field, which is how the VGAN interface works. It's very simple. You have a common ground and then 2 data lines, one for the 0 track and one for the 1 track. And that's how they are transmitting data on this interface. To send a 0 bit, just emit a pulse on the 0 wire, and to send a 1 bit, just send a pulse on the 1 wire. It's very widely used. I've never heard about it before, but I recommend a talk at, I think, DEF CON some 4 or 3 years ago. I'll put the link in the Fahrplan, where somebody talked about, a Zach Franken, I think, talked about these and how to build a man-in-the-middle device for these. And there I heard about VGAN the first time. And apparently it's used all over the place, all over the United States. All the old legacy installations have still access control panels that have VGAN inputs. So all the readers, even the readers they produce today, have to have VGAN output. This is an HID access control reader. You probably all have seen these. Even if not in person, then it's the standard reader that's used in every movie, in every spy movie. When they swipe a card and steal a card, you will always see this reader. It has an LED bar up here that normally lights red and will light green for a short amount of time if you swipe a correct card in front of it. And it has a lot of outputs, and 3 of these wires are still the VGAN interface even today. Even the most modern readers, HID produces readers that have biometric sensors and so on, and all of these will still have a VGAN interface and will still output the 26-bit VGAN identifier if they read correctly a card and made a biometric identification. That's what the other talk by Zach Franken was about. He built a very simple man-in-the-middle device to just sit on these 3 wires and replay data that has been recorded before. This is the standard, de facto standard VGAN format. It has 26 bits. Part of it is the facility ID, which is 8 bits, and just so that you can distinguish different facilities in your company and not have the same card numbers everywhere. And it has 16 bits of card number and some parity bits up front and behind. That's the de facto standards, of obviously not standardized in a proper standards body, but it's what everybody uses, and every system, even to this day, still supports output and input. Yeah, Milos activated the VGAN reader. Yeah. Yeah? Yeah, it's yeah, that's what HID calls beep and blink, what they particularly love. Easy installation, you just put up the reader and it will beep and blink if any of the cards that HID sells is put in front of it. And then it will output the identifier stored on that card on the wire. That was the case for the old cards, the HID prox cards, which we showed last year, and is still the case even for the new cards, which supposedly have DES and triple DES security. You just swipe it in front of the reader and it will output the identifier that's stored on the card. regardless of whether this identifier is authorized for the facility. That's the job of the access control panel. Yeah, the format, you cannot only have the the standard vegan format, but other different formats. HID takes very high pride in its support of formats and multiple formats. And format is another word that you probably wouldn't associate in the context as it's used in HID speak. A format is basically just the mapping of this bit string that I showed you, which can have other bit length, the bit string and the mapping between bit string and field. The fields are, for example, the facility ID or the card ID, or you supposedly could have other fields in there. Checksums, mostly only parity, and the format also defines which kind of parity and which bits they apply to. And yeah, HID treats formats as a security measure. I showed you before here the old standard is 26 bits, and HID's new standard is 35 bits, so it's a huge improvement. But there are different other formats which even have 44 bits, which is really much, really a lot of bits. I don't know if you can even imagine having 44 bits. And HID treats these as a security measure. HID has best practices and access control paper out there, which is somewhat low on the technical content, but provides for good humor. For example, this quote, I really love this. Don't succumb to the argument made by alternative card suppliers that proprietary card formats are more expensive and are an attempt by manufacturers to keep you from buying cards from open sources. The use of proprietary card formats offered by an OEM or one that is exclusive to a particular site is a desirable best practice. Cards with proprietary card formats are much more difficult to fraudulently obtain. Of course, their format obsession has nothing to do at all with vendor lock-in. It's all about security and a desirable best practice. They even have a particularly expensive proprietary program, their Corporate 1000 program, which is their term for custom formats. That's why I mentioned the 35-bit format. That is their standard length for their custom formats. HID will create a custom format just for you, just for the customer, provided you pay enough money. And it will randomly assign the field mapping specific just for this customer. But HID will assign and manage the format internally. And you then have to order new cards through HID by mentioning your custom format, and then you will get new cards using this special format that only you can get cards for, only from HID, only for the exact amount of money that HID charges you for that. There seems to be a large and very unhealthy obsession with these formats. About 50% or more of literature on HID and HID related stuff seems to be about formats. For example, they have a how to order guide. It's like, I don't know, 80-page PDF where you can read all about formats and how important formats are, and specifically custom designed part number just for you, just for your format, where you can order more cards from HID. One neat thing is that they specifically mention that the field mapping, the fields do not need to be in order, do not need to be consecution one after the other in the field, but they can be randomized. And I'm not sure if they realize that, but if you randomize the field layout, then it might be possible that two different cards from two different formats might produce the same 35-bit string, because the fields are in different order and may have different contents. But if the facility ID of the one is the card ID of the other, they might actually create a collision without anybody realizing that ever. Because the format, again, is not stored on the credential, it's just something configured in the panel. That's also something they consider to be a security feature, that the cards do not store which format is stored on them, but so an attacker that finds a card cannot find out how the bits map to, how the fields map to the bits. That's a security feature, according to HID. Yeah, HID offers credentials in different formats. Or for I-class at least, they have these ID1 cards, pretty standard. They have some cute round tags, and we have here these hexagonal things which all use the same electronics inside, more or less. They have different logical organizations. They either have 2K or 16K bits. That's again another neat thing. They talk about 2K and 16K and mean bits by that. Every other vendor, for example, MyFair, talks about 1K and 4K, and 1K of course sounds less than 2K, but 2K bits are only 256 bytes, while 1K bytes are actually 1,000 bytes. So. And they can be organized in 2 or 16 areas. At least the larger one can have 2 or 16 areas. I'll talk about the areas next. The smallest addressable unit on a tag is a block of 8 bytes. Everything is organized and addressed in blocks of 8 bytes. Multiple blocks make up an application area, and 2 application areas are on 1 page. The 2K card only has 1 page, and the 16K card might have more pages. And in the literature and the documents for the serial protocol, I found reference to a 32K card, which then has 2 books of which each behave as a 16K card. But I haven't seen that in the how to order guide, so I'm not sure if you can actually order that. The page layouts are all pretty similar to this one that is from a 2K card, which has 2 application areas. In the block 0, there's the card serial number, which other people call their UID, but HID calls everything card serial number, even the MyFair Classic UID. Then there is a set of flags I'll discuss on the next slide. This is a secure stored value area, which you actually can't use on this tag. You can only use that in a 16K tag, but it's there anyway. Then there are 2 keys that you can't read. If you try to read them, they will read as FF. An application issuer area that is unspecified in use. It's just, it's there and you can read it. And then there is the area for application 1 and an area for application 2. The space utilization is actually flexible. In the flags, you can customize the memory assignment. You have here the application limit, which basically is just the block that sets where the border between these 2 areas is. If you set it to 0 or up here, then everything is application 2. And if you set it to 31 or higher, everything is application 1. And there are some one-time programmer bits. That's not very interesting. There's a write block that wasn't set in our cards, I think. You can make the card read-only if you want to, which would have been a good idea. And then there are some bytes that specify which kind of card you have and how the memory is organized on that card. Pretty much not interesting for most of the time, just to recognize what kind of card you have. Yeah, the HID access control application, on the other hand, is special. It's the first application on each tag, which means it's the only page, the first application in the only page of a 2K credential, or of the first page on a 16K 16 credential, or on the first book on a 32K credential. Its application limit is supposed to be fixed to 18 or hex 12. And the secure stored value area is not available, or supposedly not available on these cards. That's what the documents say. If you have a card with more than 2 application areas, you can use the secure stored value area of the later application areas for your first application. In this case, key 1 is supposed to be the debit key, and key 2 is the credit key. We haven't tried if that's actually true, but let's assume it is. That's how the HID access control application looks like. Also from their documentation. The size is fixed. These here are not used. They are always set to 0 in our cards, I think. The first block is some kind of directory. Then there's the access control ID. They have a field for a PIN, which apparently is also not used or wasn't set in our cards. And as I said, these are not used at all, currently at least. The HID access control ID is actually the Vigand ID I talked about before, or whatever other format you have. We actually saw that these readers have a serial interface and will send out the ID of the card they just read with some additional formatting. They have preceding, padding, and a start bit that says here's the end of padding, and actually it's stored in these fields in exactly the same format that's output on the serial interface. So this is just the raw bit stream that's output on the serial interface when you put the card in front of that reader. Yeah, now Milos will talk a little bit about how these blocks are supposed to be secured.
Test.
Better. Now even I hear you.
So the biggest problem we had on the beginning was to find actually out what we want to break. HID really makes a big deal about not only different format, but also different ways to secure your system. So mainly we extracted three major types. The first, basic security, let's call it standard security, interestingly uses two keys, one for authentication. If you don't know this key, the card won't talk to you. So this key is used to unlock the card and to talk to the card at all. Interestingly, in standard security, the same key is used all over HID. So if you have a standard security system, you have these two keys which secure installation. If you're unhappy with that, then you can switch to the next higher level, which is high security, where you can get a system-specific key for your installation. There are basically two ways to do that, or three ways. One way is you simply ask HID to provide you with the keys. So HID will know about your key, your vendor will know about the key, and usually you won't know about your own key. That is used as an interesting way to log in a customer. So you can't easily switch from one vendor of cards to a second because you don't know your own keys. I know several people which have exactly that problem and currently trying to fight it out in court. The interesting thing is that you could generate your own keys, but this is something which seems to be disapproved by HID lately, as the tool you need for that is the card programmer. And it seems that HID discovered that there are some security issues with their product, so they stop selling this programmer, so you can't buy such a programmer anymore. You can just lease them, and several vendors told me independently that there is incredible amount of paperwork involved and a lot of money till you arrive at a point where you can obtain a programmer to program your own card. So the usual way seems to be, if you want high security, you ask your vendor, you receive a programming card, and you simply buy from any source, maybe probably from your vendor as well, a standard security reader. You swipe the programming card, and the reader turns high security with the new key, and optionally sets the reader in a temporal key rolling mode, where the reader detects standard security cards and sets the high security key. So basically that's a one-way thing. So you swipe the configuration card, swipe like 100 of your standard security badges, and afterwards the reader is fixed in high security, and your badges only will authenticate to this particular reader. And note that you don't need to know your own key there as well. So this seems to be desired practice. As for all standard security devices, the same keys are used. So one key for authentication, one key for encrypting the data. So the first key is a simple 8-byte DES key with effective key length of 65 bits. And the second key is a 16-byte triple DES key. As the same keys are used, it's obviously a big incentive to retrieve these keys, as it would give access to all standard security installations, which seems to be, to what I heard, the most common case. To do so, we need obviously only to break a single reader. So HID talks about a mechanism that a card-specific key is derived, which sounds incredibly cool because you have then as many keys as you have cards, but keep in mind that obviously each card needs to be read at a particular reader. So therefore, the master key needs to be known by the reader, otherwise the thing won't fly. So therefore, the keys need to be in the reader, no matter what key derivation goes on. Older version of these readers are easily accessible over eBay, so you can't just go into a market and buy these readers. You usually have to go to your vendor. But old readers from previous version, outdated version, you can have on eBay. And as the key is the same, it doesn't hurt to have an old reader. The particular reader we received was the RW400 with this particular type number, and this is how it looks. So basically, you put this plate on your wall, attach a reader, and just clip on the cover, attach one screw, and that's it. And several wires are involved, which are neatly documented on the back of the reader.
HID recommends to use a security screw.
Ah, yeah, a security screw. We want to have security. Yeah. By breaking open one of these readers, because they are so incredibly cheap, something like $10 each or whatever, I simply broke open one of the readers, and we interestingly find a PIC microcontroller there, which is not something you would expect from a professional product, but here it is. And suddenly the 6-pin interface on the back, which is security sealed with tape, with black tape, so attackers won't find it. Turns out to be actually the in-system programming connector. And as a measure of security, so nobody will be ever able to find out how that works, they swap pin 1 and 3.
Pay no attention to the connector behind the tape.
The interesting approach was that, as this was getting boring, we obviously would have the possibility to send in this PIC controller and have it uncapped for something like $100 and receive the firmware. So this, I think all you know, the services. It's not a big deal in our days anymore, but we want to keep up a good spirit and try to break into the thing on our own. So what I discovered actually, 0-day, ta-ta, that several PIC18F controllers, you can circumvent the copy protection fuses. It's actually very simple, and if you read the datasheet carefully, it's clear as crystal. Yeah, they properly set the fuses, and if you connect your programmer, it says all protect, so everybody is happy, and if you are straightforward, you need to erase the thing to access anything on the device, so it's not big fun. But if you read the datasheet of the PIC18F452, the webpage, they have a nice link to the programming specification of the device. So it turns out to be that PIC microcontrollers have, I won't go deep into that, there is a paper additional to the slide which you can already download on a webpage that is completely described. They have basically an interface where you can send PIC opcodes which are executed on the device, and they protect it against obvious attacks where you use these opcodes to read from flash memory. So this is not possible. But the datasheet clearly states that you can erase single blocks, and if you erase the single block, then the single copy protection bit is erased as well. So there are several erase commands which are described in this program datasheet. One is erase all, which is the one which you usually are confronted with your standard programming software, but there are something like 6 more bulk erase commands where you can erase individual pages. So obviously this doesn't bring you anywhere because you erase the stuff you're interested in, but you can erase single pages. So what is easily possible is you erase only the boot block, put your dumper firmware there, it outputs the remaining flash on the UART. You have 90% of the UART, including the EEPROM. Ta-da. The sources for the dumper are also available in the additional paper. We also, because we want everything, we don't want only 90% of it, we want to dump the bootloader as well. So basically, it's a variation of the heap spraying attack. So we erase everything except of the bootloader, put the dumper on the very end, and we hope that the boot block will jump at some point across this 200 hex boundary, enter a long row of knobs, which is a result of a race, travel to the end of the flash, outputs again everything, and we have the beginning of the EEPROM as well. So I find a nice tool which makes it easily possible to convert these binary files into inter-hex files, create a unified inter-hex file, which you can now easily flash back into the PIC microcontroller. And by doing that, you, at that point, simply unset all the nasty anti-debug stuff. So you enable debugging, disable watchdog timer, and suddenly you can use MPLab software to single-step debug the whole reader, which is obviously cool for understanding how the system works, because remember, no documentation on that. So it's then easy, for example, to dump the EEPROM changes in process, so you can pause the device, change a byte, have the device running again. As the EEPROM is very small, it's only 256 bytes, random keys can be easily spotted. Here in this example, they're intentionally grayed out to protect existing standard encryption customers, because this would allow attackers to copy and clone cards. We don't want to do that. But it's easily to find these keys because you have 4 random looking blocks. So one of them is this one, which I don't know what it means. But here is the triple desk key, and here's the 8-byte authentication key. And by simply poking into these blocks, you immediately see what happens. So if you poke into the authentication key, obviously your existing card won't authenticate anymore. So therefore you can narrow down which key is which very quickly without analyzing kilobytes of PIC code, which sucks. When HID stores keys into the reader, they are permuted. We luckily found as well HID documentation on that. How the permutation process is simply building a 8x8-bit matrix of the 8-byte key, turning it 90 degrees, and XORing, creating XOR checksum, which will replace the last byte. This is also explained in detail in the paper. So with that, we can reverse permute the key and use it in standard readers suddenly. As HID was very nice and kind to us and provided us with a perfect attack tool, which is nice, cool, you can show it around, and it, according to documentation, isn't able to write the HID control application, because then you could copy cards and nobody wants to do that. So they have the authentication key stored here. You have to apply for a 16-byte key to even talk in this mode to the reader, and then you can only read using the stored key, but you don't know about the key, and you can't write. So this is possible if you sign NDA. But as we didn't want to sign an NDA, we simply took out the keys we retrieved, stored it in the reader, and as now the reader thinks, hey, this is your own key, so you're allowed to do anything with the key. You can even write. We're suddenly able to write in the HID access control application. And as they kindly provided us the triple desk key as well, we are even able to decrypt the data stored there. So here you see our weaponized version of I-class reader. That's the card serial number, configuration block, application issue data. And here, this is normally not visible if you use a standard reader. This is all FF'd out. But if you use the proper key, you will see the data, but it's still triple desk encrypted. But it's only one checkbox away to decrypt the data. And yeah, you can do everything, including writing, which isn't supposed to happen in our opinion. As interestingly, so I don't know if Henrik already explained it, but you see one very obvious flaw. So this should never, ever, ever, ever happen. You have two blocks with the same content, and encrypting, the encrypted data is the same. So they missed not only to encrypt the data block specific, so you can easily move around encrypted blocks and thus modify the data without knowing the triple desk key. But interestingly, this also works across cards. So all other cards have the same encryption, and you can simply copy a block from card A to card B without decrypting it, and it will work. So some very strange things were suddenly obvious once we could read this area. But Henrik will tell more about that.
Yeah, just need to see. I think I have done a stupid thing. I was trying to magnify that, and apparently that's not supposed to happen. Just one moment. So, yeah. Yeah, now we know the trick. Sorry about that. What was the trick again? Ja, ja. Es ist nicht ganz wahr, aber so. Nochmal. I blame Compass.
Tu es einfach reinschieben, ohne Vollbild.
Es geht nicht ohne Vollbild.
Nein, also rüberschieben.
Es geht gerade gar nicht. Kein Moment. Let's see. Yeah, sorry about that. Yeah, sorry. I've never tried the magnification before on the Intel screen. It works perfectly. So yeah, if you see that, you know it's bad, bad, bad. We didn't see that at first. At first, we tried standard technique. If you have an unknown RFID system, you rip out your sniffer and see what happens. We have this incredibly cool Proxmark 3 device, which is a universal RFID sniffer. The sniff you see here is actually not derived. We did not use the Proxmark to get that sniff because it's still kind of unreliable sniffing from the air. But instead, we opened one of these readers and found the traces on the PCB, the traces where the raw data signals were traveling, or at least the envelope signals, and recorded them with a logic analyzer. But there's also code for the Proxmark that I'm publishing, and you can use the Proxmark, you just will lose some frames sometimes, and by using the other technique and sniffing on the contact-based wires, you will not lose any frames. That's why I'm displaying it here for overview purposes. Yeah, what you see here is output of my tool, which I think will make public too. The first line, ignore the first line, it's a timing, that's also timing. This is who sent that frame. That's the number of bits in that frame. And then there are some flags. You'll later see a CRC. If the CRC check doesn't match, then it will print a C in this one. And some of the frames do not have an end of frame indication. That's why the unended signal here lights up. Yeah, and what happens, that's an entire, well, almost entire transaction that's actually recorded from this reader or one like these. If one of the standard security tags is put in front of it. Explanation. For the start of the trace, obviously, is the selection procedure. The AIR protocol is not quite ISO 15693, or actually not at all. I didn't recognize it at first at all. Milos, I think, had the idea to see whether it would be 15693. I was looking for 14403 or something similar. But the lower layer is the same. The bit encoding, the start of frame, end of frame, and bit encoding are 15693, and everything above that is something else. These 0A commands are some kind of polling. Is a card in the field? And if a card is in the field, it will respond with a start of frame indication, with no end of frame indication, which isn't supposed to happen in my book at least. That's why it says 0 bits and not ended. If the reader sees that there's a card in the field, it will send a different command. The card will answer with a fixed string of bytes that's fixed for each card and has a correct CRC. I'm not sure, I don't know where this string of bytes comes from. It's not a UID, I have no idea where that comes from, but it's fixed for each card. Then the reader sends an 81 command with this string of bytes, to which the card will respond with its own UID and CRC. You can easily recognize that's a UID, I hope, because it ends with E0. All the ISO 15693 UID start with A0, E0. Yeah, after that, there's the authentication. Those of you who have photographic memory probably have noticed that I omitted a command. This 84, we have no idea what it's for. It's only emitted by that reader, or by these readers. It's not emitted by the OmniKey reader, and it doesn't get any response from the card, so I'm just ignoring it. The card is ignoring it, apparently, too. This 880002 command seems to be the command that starts the authentication procedure. The card answers with the stored value block. You can easily recognize, because in the HID world, the stored value block always has one side FF, and the other side is the stored value, and it alternates between these two. I've read, I already forget where, I've read the explanation behind this, something like, it's about atomic write procedures or something like that. It's always alternating between these two when it's writing. And yeah, so that's the stored value block contents. If you remember, it's stored in block 2, so I'm fairly confident that this is actually a block number. So it might be interesting to build a custom reader to see what happens if I submit the command 88 03, where the key is stored, for example. Maybe let's see what happens then. Yeah, and afterwards the command 05 seems to be the authentication command. Then there is some strange from the reader and some strangeness from the card, which seems to be their whole authentication. I'm talking about that a little bit more later. These readers seem to also write the stored value block. That's why the next command is 87, which seems to be the write command. Block number 2, and write the new stored value block. It's decremented by 1. You see here AC, before that it was AD. So it's decrementing it, storing the new decremented value, and the card responds with the new block value, and you see it has swapped the two words of this block. And all these, from here on, all the frames will have a CRC. And then the reader proceeds with reading the actual card contents. OC seems to be the read command, followed by the block number, followed by a CRC. And then the card responds with the block contents. This I think is the configuration block, the flags with CRC. So the authenticators in the system seem to all be 4 bytes for everything. There is no random number from the card, which, as most of you will by now recognize, is a bad idea. Which means also you can replay transactions against the card. Although the stored value block seems to go into the authentication, that's why it's read before each authentication. These readers decrement the stored value block, and that seems to be, is probably the reason why HID claims that you can't use the stored value block in the HID access control application, because these readers will then decrement it. But our OmniKey reader completely leaves this block alone. It just reads the block and uses this value. That's why most of our cards have very high values in this block, because our reader just doesn't decrement it, which then means you can do an easy replay on these cards because there's no random number from the card. And if you've sniffed authentication token from a reader, you can just replay it and the card will accept it again.
One small note here. The big advantage of the OmniKey reader is that it doesn't know anything about all the special formats used for normal access control readers. So if you present a normal access control reader, you can't, for example, configuration card, you can't do anything because it will immediately reconfigure the reader and render your reader unusable. But the interesting thing is you can present anything to the OmniKey reader, and it doesn't pass it on its own, but it's just a normal reader where you can read and write stuff. So the big advantage is that you have a tool which isn't affected by the configuration card, but you can read and write to it. So this is, again, a big advantage of this.
That's basically one of these coveted programmers, but for a lot less money. This one is free because I borrowed it from my university. The random number from the reader is also 4 bytes. It seems to be in various bad shapes. These readers have, for example, have a serial protocol. You can talk with them and convince them to not only operate as a normal DOR reader, but also to just operate on demand and read cards. And if you do that, then the random numbers seem to degrade extremely. I think I've seen somewhere they were all 0 or all FF or something like that. The OmniKey is similar. We have programs that use the OmniKey to read, and for these, the first 2 bytes of the random number will always be 0, and the next 2 bytes, or the only other 2 bytes, seem to be incrementing. Looks suspicious. I haven't done proper statistical analysis, but it seems to be not very convincing, at least to the naked human eye. That's also how I know which part is the random number and which part is the authenticator, because the other 4 byte in the reader command are always completely, or look completely random, so that's most likely an authenticator. And then there's another 4 byte authenticator from the card that's somehow related to this. For writing, there's also an authenticator after the write command. Again, it's a 4 byte authenticator. And at least when writing key blocks, where I observed it most often, it seems to depend on the previous, on the current and the new contents. So if I write a key to a key block, then the authenticator is different depending on the new and the old value in that block. The writing also has some special strange behavior. As I said before, when writing to the stored value block, it will swap the writes that you write, the actual order of the blocks. And if you write a key, then it will actually transmit the XOR of the current and the, I think it's an XOR of the current and the next key, because if I write the same key again, then the value that is written is just a string of zeros, and I'm not sure. I don't actually believe that their standard authentication key is all 0. At least I hope. I haven't seen it. Milos has the key. And you probably noticed there's no message authentication at all, except for write commands. The card responses are all unauthenticated. They do mutual authentication, and everything that comes from that radio field probably belongs to the same card that did the authentication. There are some CRCs on the card responses, but those use the same polynom as the ISO 15693 CRC, but have some custom post XOR magic on them, which doesn't seem to have any reason other than being their own custom CRC that nobody else knows about. But of course, it's easy to figure out because you just need to compute a CRC the normal way and then XOR with the whatever you get from the card. Yeah, HID security, what is actually there? The authentication key is based entirely on the card serial number. There are no other inputs for the key derivation. So, and the card serial number is not bound to anything besides the authentication key. There, especially the card, the actual Vigant or format content is not bound to the authentication key, which is kind of bad. HID has this best practice security document out there where they rally against using card serial numbers and claim their own Vigant identifiers are much better and everything, and also more convenient because you can group cards by identifier from 1 to 100, for example, while their UIDs are completely random. Apparently, they assume that the security panel is a very bad implementation because normally, at least if I would implement that, then each access control decision would just be a database lookup. And the database should basically not care about the format of the identifier, but apparently all the panels that HID talks to are very bad and cannot handle randomized identifiers. As Milos mentioned, the blocks are encrypted, even with triple DES, but they use ECB, electronic code book. They have no binding on the card serial number, they have no binding on the block number. If you encrypt a string of 0 bytes, then it will always have the same encrypted value, these 2A, D, whatever, that you saw before, which is obviously bad. You can make verbatim copies of blocks. You can transfer blocks between each other, and you can transfer blocks between cards willy-nilly, and which means the content encryption might give you some slight privacy. It doesn't give you privacy, really doesn't give you privacy because it's always the same. It's still an identifier. It might not be the same identifier that's used on the wire, but it's still an identifier. But it doesn't help you at all against impersonation. The missing message authentication means that you can perform man-in-the-middle attacks, and that leads to privilege escalation or worse. You just need one of these tokens, that Milos took. You just need one of these tokens to use as an oracle. Let this token perform, or at least in standard security, let this token perform the mutual authentication, and afterwards you can use the proxmark in the same field to do the further communication, and then you can do whatever you want. You can reply with whatever block contents that you want. Which means that standard security is pretty much broken beyond repair. It's on the same level, approximately on the same level as HID procs, which is supposed to replace, and it's on the same level as logic prime. Once you have all the secrets out of the system, you can break into arbitrary places secured by the system. There are some open questions. We haven't yet looked, because as Miloš mentioned, there's a lot of PIC code and nobody wants to look at PIC code. We haven't looked at the exact algorithms for the key derivation and authentication. Well, that's why Miloš gave you the code and the technique to extract the PIC code so that you can look at the PIC code and maybe share your results with us. We'd be very much interested in these algorithms so that we can build custom emulators for both reader and card, which means we could do a lot of fun things. We could try to replay write commands, for example. If you sniff a write command, you can just replay, or I think you can just replay it. And we could also try unexpected commands like this 88 I told you about before. What would happen if I just put in a block number here? Will this then start an authentication against this block? Can I choose the stored value block that I want to authenticate against, which would mean that this reader decrementing the block doesn't provide any security at all if I can just choose one of the blocks that is always set to FF? Or can I use it to completely dump a card? Those are open questions, and by no means, I'm not implying that by no means, so don't sue me if it's not true. One of the things I want to mention is that obviously security here is bad, and they probably didn't ask anybody who knew anything about anything. They just did what we always told them to do. If you remember our last talks, we always told them, use standard security algorithms, use the triple DES, use AES, use mutual authentication, and that's what they did. They used mutual authentication, they used triple DES, and they used it in a way that even one of the companies that produces cards, not this one, maybe we talk about it next year, likes to draw diagrams. They have a card here, and a reader, and a host device, and they like to draw little arrows between this and annotate the arrows with like IES and triple DES. And that's what HID also does. They have triple DES the whole way from the host to the reader to the card and back again, but in a way that's completely useless and completely insecure against impersonation or direct copying. And that's how we want to end the talk. Here is the paper Miloš kindly wrote for you. That includes all the firmware extraction stuff and a little bit more. And now I don't think we have time for questions. Sorry about that. But,
Outside, we're going to have questions.
In this room, for the people leaving this room, please use the door in the back. Thank you.